Hi, this is Taylor Daring, and this is Physics 2211 Lab 1. So in this lab, I graphed the position of a water bottle moving with constant velocity, which I'll show you that video in the next slide. But basically at every frame that it moved, I marked where the position was according to the axis that I set, which I put the origin at the initial position of the water bottle. And Tracker made a graph of that. I also made a computational model using GlowScript and Newton's law, the momentum principle, and I compared the expected results to the actual outcome. To create this predicted model, I used the position update formula and the velocity update formula, which you can see here. And to use these formulas, I had to calculate the average velocity, which in order to do that, I had to know that the forces were constant. So the average velocity was equal to the final velocity. So I could plug that into the position formula. And in order to find this average velocity, I just used the change in position over the change in time, which comes out to negative 1.301 meters per second. So when I used these formulas in Tracker, for the velocity update formula, basically since there's no net force, the velocity final is equal to velocity initial, meaning that for every single time step, the velocity is the same, which is what the goal was. And then for the position update formula, it updates every new position based on the average velocity that we've calculated and the time step, and adding that to the initial position. So using this, we made a graph that we compared to our observed graph. As you can see, the water bottle here is moving only from the right to the left direction. It won't be moving up or down, which would be the y direction, so the only thing that we'll be analyzing is change in x position. So here we are looking at our data in Tracker. At each frame, it would pause and I recorded the position of the water bottle, so we are just looking at the change in the x position. As you can see, the initial position was at 0, and then as time progresses, it decreases or goes to the left in position. You can also see at the top right graph that as time increases, position decreases at a pretty constant rate. So change in position at each time step is the same, which shows that it does have a constant velocity. Here we have the code that I created in GlowScript to show the computational model for my predicted position for the water bottle. So I've marked with these little red arrows all the things from the original starter code that I've changed. So first of all, we have the mass of the water bottle is 0.3203 kilograms. And then I have the initial conditions of the experiment. So the initial position vector is the 0 vector, since the initial position is marked at the origin of the axis. And the initial velocity, again, is the average velocity, since the forces are constant. We can use average velocity as the same as final velocity, which is change in position over change in time for the x-axis. And then for delta t, I changed that to 0.033 because that's the change in time of all the frames in Tracker. And then for net force for this experiment will be 0 since the velocity is constant. And then I have the velocity update formula and the position update formula here next. So after each time that it loops, it changes the position for each time step. Here we have the experiment versus the model's position. So the green line we have the model that I created on GlowScript's position, and then the orange line we have the observed position that I found using Tracker. So there's a little bit of a difference, but for the most part they're basically very similar. One of these reasons is that it's hard to ensure constant velocity as there are other forces present in the experiment. For example, I gave the water bottle an initial push, so an initial acceleration is present. I delayed starting Tracker for a few seconds to avoid this error, but I can't guarantee that it didn't affect it. Also, we assume friction is negligible, but the reality is there is a force acting on it because the water bottle will eventually slow down and stop. But still, my recorded results and the model results were very similar. There are several reasons why there could be differences, as we just discussed, but we still see Newton's laws in action due to such similarity. Now, for what if and what does it mean, we can look at what could have happened if I changed how the axis looked. What if they were flipped? In this case, the magnitude would stay the same and just the direction would change. And for what does it mean, we can conclude that even though many forces were probably acting on the water bottle for this 0.7 seconds, and we don't know the extent to the pushes and pulls of the forces, we do know that the velocity is constant, and thus the net force for the whole system is indeed 0.